Good afternoon, everybody. So this is a little bit different of an experience, and nobody was anticipating any of this, but I think in moments like this, we do the best that we can, and we're all on track to be very successful. And so it's these sort of moments in life where we prove what we're made of. And so we're going to carry on as though we were all in class together, and I know that that's a little bit artificial in these lectures. Won't exactly have that bi-directional communication that we really get from a classroom. And I think that's extremely important. So I would like the chance to interact with all of you. I'm still available over my email, and so I would be willing to do one-on-one meetings if necessary. And so you can contact me if you want to sit down and talk about the materials. I'll be available for the duration of the semester. Also, we're going to have some live broadcasting as well. So starting on Monday, I'm going to show up, and I'm not sure which room I'll be using. It doesn't really matter, but I will be live broadcasting my lectures. So I'm going to be using YouTube Live for that, so everything will be disseminated through YouTube. And that'll give you the ability to use the chat interface, and you can ask me questions throughout that. We'll find a way to make that work. I'll probably start out with a helper that can read the questions to me, and later on I'll get savvy enough where I'll be able to take care of it myself. We will also be doing online office hours, so our review sessions, our recitations. So I do like the opportunity for us all to be able to hear each other's voices, all of the questions. I think that's part of learning. And so we'll be using Zoom for that. And I'll probably start up in about a week or so where we can do our typical recitation section. And so I'll be able to hear your questions, and so will everybody else. And I'll try to answer them all in real time. So 3 mechanisms here. We're going to use YouTube Live. We're going to use my static camera that you're viewing me on now, and that'll give you the ability to zoom in on the board. So I'm filming all of these lectures in 4K, and so if you're trying to go back and understand what I've written precisely on the board, you can zoom in on that and take still shots yourself. So we'll be posting high resolution video for you. And then we're also going to be using Zoom for our typical review recitation sections. I think with that and constant email communication, we'll all be in pretty good shape. Maybe better than before, I'm not sure. Last point of business is testing. So on the midterm that I handed out yesterday, that was my midterm from 2019. I didn't modify it. There is a funny, peculiar thing that shows up in problem 4, and it's intentionally written that way. Some of you will know what to do to that statistic to make it better. I had intentionally done it where at first I had written it down and I said, oh, I need to go back and modify this. I wrote it in wrong, but I thought it made the problem kind of clever. It's still an estimate of what you're trying to estimate, but it's not very good. We'll be talking about that later. That's where we'll be jumping into next week, is what makes estimators good. So we'll be studying a couple different paradigms. So method of moment type estimators, likelihood-based estimators, Bayesian estimators, and we'll be asking a lot of questions about those estimators. And what we'll find out is that as long as you have a good estimator, it has properties. How you derive it may or may not matter to you. So we'll be talking a lot about that. Is what are these paradigms? What are they good for? Is that structure worth anything at the end of the day? And so my opinion is yes, it is. Some other people's opinions that I've talked to say no, it's not. It just matters how well this estimator works. It doesn't matter how you got it. And so I sympathize with that perspective. But we'll be talking about a lot of stuff, and I'll try to build in the stories as we go. We'll have the benefit that we're not on a strict 50-minute schedule. So sometimes I might go over a little bit or I'll come under. And so you can kind of fast advance through the stories if they bore you. With that said, I want to pick up with where we were last time and talk about the negative binomial distribution. I had made an error in the last lecture, so I want to address that error. And then I want to come around and finish up chapter 6 stuff, talk about ancillary statistics, talk about complete statistics, and talk about Basu's theorem. Interestingly, on Basu's theorem, I'll tell you what it is. Towards the end of this lecture, I had asked somebody once upon a time, maybe about a decade ago, what should we be building into our inference classes that we weren't building in before? And people have a wealth of ideas. This is the new material I'd like to present. And I asked, what would you get rid of? And I've gotten the answer from several people that this is what they'll take out of their class. Things like that, Basu's theorem. I still want to talk about it. I think it's interesting. Certainly an interesting mathematical statement, but I don't know if it helps you practice statistics any better if you can actually prove this theorem or figure out which statistics are complete that Basu's theorem addresses. So I'll try to disentangle minimal sufficiency from ancillary statistics, and we need a building block called a complete statistic to make that bridge between the two. So before we go into that, let me just come back around to where we were last time. We were studying the likelihood principle, so if you want to review that lecture, I think that was the 6th of March. I had made an error, and I had written down the negative binomial distribution incorrectly. I did put this -1 here. A couple people were calling for it, and it was an accidental mistake that I made. You'll notice that in my example in the likelihood principle, the number of successes and failures were exactly the same. They were both 5 in that data set. So that's what created the confusion. The -1 should have appeared right here if we use successes over here. So I wrote down y -1, and y and the number of failures was y. The number of successes is s right here. And so s plus y equals n. And I've written that down in a funny way right here. So just some relationships between the number of failures y, the number of successes s, and the total number of samples n. I'll point out for a negative binomial distribution, the number of failures is random, the number of successes is fixed, so that means that n is also random right here. So the negative binomial distribution is this right here, but you can write it like that. So I had a mistake where I wrote y -1, and it should have been the number of successes -1. They turned out to be, in that case, exactly the same numbers. So see if you can get that right. Try to study up on the negative binomial distribution. Y right here is random, or n is random, depending on how you want to talk about it. So the number of trials is always offset by the number of successes. And so how many trials would we have to add up to s fixed successes? Well, that would start counting at s itself. And so if you use this parameterization for the negative binomial distribution, n starts at the number of successes. You just write that down. So n is an element of successes, successes plus 1, so on and so forth. And so again, a negative binomial distribution is well described by the number of times I flip a coin with probability p, and the number of trials that I need before I see s successes. So I have to flip the coin at least s times. And this is just parameterized a little bit differently, using the number of failures. So the number of failures is also random as well. And that can start counting at 0, 1, or 2. But if you parameterize it using s as the random variable, then you're going to start counting at s plus 1, and so forth. So they're just shifts of each other. This is an entirely different distribution. Of course, it's also a coin flipping model, but the binomial distribution addresses how many successes we see in n fixed trials. So in a negative binomial distribution, this is random, n, and the number of successes is fixed. For the binomial distribution, n is fixed, and s is random. The distributions almost look the same. Slight error right there, that was something negative. N minus S. The distributions ultimately look very similar. This part, the part in which the data touches the parameters, and I can't factorize it away, looks exactly the same in both of these distributions. So if you go over that lecture on the likelihood principle, this is the big point that we're making, that these have the same likelihood kernels, they have the same likelihood functions, but their sampling distribution is different. And so the argument in the likelihood principle is if you computed something and you plugged in N and S into these formulas, regardless of what I thought was random, should I make the same inferences about P? And I think a lot of you would sympathize that it's really the ratio of successes to the total number of draws that is important. That's the important bit. And it doesn't matter why you stopped. And so, why you stopped flipping the coin. I sympathize with that point. I do agree with that. And so, when the likelihoods are the same, you probably should be driven to make the same inferences. The likelihood principle is a stronger statement than that. It says you should. And we ended up violating the likelihood principle when we computed p-values. That is, we were summing over this distribution or over this distribution, and the random variables were different in these cases, and we'd sum over more extremity, and that's what a p-value is. So more extremity under the null hypothesis with respect to the tail direction of the alternative. And when you sum over these things, the normalizing constants being different means that you would compute two different p-values. So go back and look at that lecture and look at those p-values. One thing that's interesting about it is that in the binomial, we're summing over successes, and in the negative binomial, we're summing over failures. So the corresponding p-values to that flip the direction of the tail that you're summing over. So this sums over the right-hand side, and this one sums over the left-hand side. So a little bit to mentally chew on, a little bit hard at 9 o'clock in the morning if you're not really familiar with these distributions. We'll get into p-values soon enough. So that's chapter 8 stuff. That entails hypothesis testing, but the point in that whole example is to show you that p-values themselves are violations of the likelihood principle. Now, a lot of classicists, people that do well-designed experiments, know what the stopping rules are, they don't care. They don't think that that's a big deal. And that's okay. So I think if you have a well-designed experiment, you're probably way better off. It's in cases where you don't actually know all the mechanisms of what created the data, and you make assumptions, modeling assumptions in there. And can your modeling assumptions drive you to make the wrong conclusions? And of course, the answer is yeah. If you make the wrong modeling assumptions, you can be led astray. You can make the wrong determinations. But using the likelihood principle, if you base everything off of a likelihood type function, and you're using the ratio, the relative heights of this function right here, then maybe you don't go astray quite so often. So that's a lot of words about the likelihood principle. I'd love to discuss that more. I probably have had way too many discussions about the likelihood principle in my past. I think the way that we'll manage this conversation is we'll be looking at different techniques. I'll ask you if we violated or if we didn't violate the likelihood principle, and I'll ask you if you care. And I'm sure a lot of you will have different opinions about it. Just wanted to clarify that mistake that I made. This is not -1 in the old lecture. So you can clarify your notes. Let's turn the page and move to ancillary statistics. So I'm going to get rid of all of this. And talk about ancillary statistics. So I think I've written this down before, but let's write it down one more time. So if S, which is a function of the data, so this is just some statistic, has the property that the distribution of Sx, and I'll just be clear about this data X has n data points in there. And these data points were sampled from some distribution that depends on some parameter. So inference class is all about using this to figure out what that is. Using the data to figure out what theta is. And so if I transform my distribution, so this is not the same f right here, this is f for x, and this is f for my new random variable. So f is an entirely different function. I would have to do a transformation of variables to come up with what this function is. And since theta underlines our original distribution, we might suppose that theta has something to do with this distribution. But if this is not a function of theta, then Sx is ancillary. So that's another way of saying S of x on its own doesn't have any information about theta. And so if you gave me S of x and that's all I got to see, I can't use it to infer theta because the sampling distribution does not depend on theta itself. And so while I've written this down notationally, it just doesn't appear in the equation. So that's what an ancillary statistic is. Let's look at an example. So I want to consider this example where xi's are uniformly distributed, IID. This right here does not need to be IID. There can be some mechanisms in the data, either spatial or temporal or something like that. And so this is a true definition right here, regardless of the IID notion. Let's look at an example that has some IID stuff in it, just to simplify the point. This example is in your book. And so, let's say we knew this. Xi's are uniformly distributed, and they live between theta and theta plus 1. So that's really just this. I have some sampling distribution. It lives between theta and theta plus 1. And it's flat. So I'm just going to be grabbing values uniformly distributed in this range. So I collect a few data points. The question is how do we infer theta? What we notice is that these data points right here are the ones that are close to something to do with theta. And so as we start collecting more and more data, these 2 points will budge up against their endpoints. So if we saw a lot of data, those 2 points are going to be informative about theta. And they're the min sufficient statistic as well. So x1, that's this one, the minimum, and xn, the maximum, are min sufficient. And we went into some detail about that a couple lectures ago. Let's just look at that one more time. So I know this height is always 1 right here. by the mere fact that this has unit length and that has to integrate to 1. So the height of that thing is constant at 1 all the way between theta and theta plus 1. 0 everywhere else. So just to be clear, this is all 0 here. And so the likelihood function for theta, given all of my data, because of IID-ness, comes in through this product of these sampling densities. So I might just write down f of x, I given theta. And I think that's all true. And so we have to be a little bit careful with this, though. And so this is a common mistake. Putting in 1 right here. And that's obviously not right. And the way you can tell that this is not right is there's no dependence between the data and the parameter set. And the likelihood function is supposed to have that information in there. So the sampling distribution constructed the data. It's got a relationship between x and theta. And so we want to use this device that has that exact same relationship between x and theta. But if we don't write down theta, we know we didn't write down the relationship correctly. And so the way you want to do this, and make this right, is make this the indicator function. That xi's live where you say they lived. And that has the relationship with theta. If you want to multiply this by 1, you can. But basically, you need to just put in these bounds right here. So that relationship is written down right there. So if you ever see your parameters show up in the bounds, make sure you enforce that in your likelihood function. If you don't, you'll make a mistake. And so here is the likelihood function. And I can write this down just a little bit differently. I can write this down. I know that this is really just saying this, that the maximum is less than theta plus 1, and the minimum is greater than theta. So if you want me to write everything else down, I can. That x2 is greater than x1, or equal. x3 is greater than that, so on and so forth. And I can bury in that relationship right here, but it doesn't tell me anything about theta, because x2 is bounded by x1, and x1 is bounded by theta. And so we don't even have to write down this information, because the logical statement right here is still true. So this is just an element of 1 or 0 if the condition is true. And this is otherwise. So what's the condition? Whatever's built in here. And so this logical statement of bearing in that x2 is less than x3, that's by definition of what an order statistic is. So the bounding information just happens based off of the maximum and the minimum. So we can see that those things are minimal sufficient. Which one has more information? Well, it depends on which one is closer to the endpoint, but you don't know that without knowing theta. And so you need to hold on to both of those things, the minimum and the maximum. And this can be written is the product of x1 is greater than theta times the indicator that xn is less than theta plus 1. So those can be decomposed as well. Okay, so we've got the likelihood function, and we know what the joint sampling distribution is. This is also the joint sampling distribution as well, if I think about it when xi is random. And so the likelihood function takes the joint sampling distribution, plugs in the data, and then thinks about it as a function over theta. So same mathematical thing that I write down on the board, but an entirely different function. So this basically tells us what is min sufficient, and we could go and use the formal definition of that. That I could end up looking at the ratio of fx given theta to fy given theta. And I can say this is a constant if and only if x1 is equal to y1 and xn is equal to yn. So I'm entertaining two data sets right here, one that I've called x, one that I've called y, and they supply the same information if and only if that is true. And so certainly they provide the same information if the xi's or the yi's, but I don't need that to be true. I just need this statement to be true. So this is the constraint that matters. So that's the other direction in the if and only if statement. And so you need to rationalize that, and then you can say it's minimal sufficient. So I've just said it with a bunch of words. Okay, so these two data points have all the information in them. And I can transform those two data points. I can transform them into the range and into the mid-range. And so these two statistics are minimal sufficient as well. Min sufficient. If you go back to the definition of min sufficiency, the first one that we confronted, that a minimal sufficient statistic is a function of any other sufficient statistic. So this is a function of some sufficient statistic. It happens to be minimal sufficient. There's a bijection there, so it's minimal sufficient. So these have all the information in them. If you go back to chapter 5, they work this out in some amount of detail. And maybe during a review session, we can go over this integration, what the bounds are, but it's a simple calculus problem. I usually say simple calculus problem that I never know how to do. I used to be really good at doing calculus, and because I do it less and less than when I did when I was a freshman in college, it's gotten a touch rusty, and I bet that's true for you too. So the only way to be good at this and all the stuff that was easy is to keep practicing it. So question is how do I come up with a distribution of R and N? So let me just ask that question. It's right here already. How do we find this joint distribution? I'll use a P. Given whatever the underlying parameter is. So that mechanism generated the x's. I would suspect that this still depends on theta, and it does, because it's been sufficient, has all the information about theta. So how do we find this? A couple steps to this, and they go through this in chapter 5. Step 1 is find the joint distribution x1 and xn, the min and the max. And we would know how to do that. So we could come up with that distribution. The way I've told you to remember how to do that is draw a picture. So you might call this the ith order statistic, the jth order statistic. I know how many things are right here, I minus 1. I know how many things are here. I know how many things are there. I know how many different ways that I can permute everything. And I know the probabilities that they would wind up in these bins. So this is just f of x right here. This is 1 minus, and this is for xi. here, and this is 1 minus f when I plug in xj. And this is the difference between f of xj minus f of xi. And we can permute these in all kinds of different ways. So we've gone over that lecture, so refresh your mind on that. But we can find this joint distribution, and we can write down what that looks like. So cap f is really easy to find, because this is just a uniform distribution right here. So we're just integrating over this thing. That couldn't be easier. So step 1 is easy enough. Step 2 is to transform. x1 in xn, 2 r in m, the range of the mid-range. So once you do that, you'll come up with this distribution. So after you complete these 2 steps and give it a whirl, you would wind up with the joint distribution of r and n given theta is equal to n times n minus 1 and this is going to be r to the n minus 2. And then I've got to say where everything lives. And so the range can live between 0 and 1. Kind of already know that. That part's easy to conceptualize, that the range is between 0 and 1 because this has unit length. But there's a relationship involving theta that defines where the mid-range lives. And so the mid-range lives between theta plus r over 2. This is theta plus 1 minus r over 2. And so there's this relationship. I'll point out that this is a straight line, and that's a straight line, and they intersect each other. So this is the range right here, and the mid-range lives between something that's bounded using r and theta, and it has to do with theta. So go through that simple calculus exercise. I think when we're adjusting the bounds in these multidimensional integrals, that's where students usually get confused. And so in the future, I will ask you to derive this at some point. But again, that problem's in chapter 5. There's a slight difference where they let this be 0 and they only put theta on the right-hand side, but it doesn't change the technique in deriving this integral. And so that's our distribution right here. And we'll notice that it involves theta. Still has information about theta, but it's over in the bounds. So it makes this problem a little bit peculiar. Okay, what we're going to convince ourselves of in just a moment is that R is ancillary. The range itself is ancillary. And we could have conceptualized that already. I've got these data points in here. And these 2 points are the informative points. They're the minimal sufficient statistic. And I could shift this whole distribution around. Theta is acting as a shift parameter. And so the range, or the variability of this distribution, doesn't tell us how it's centered. So the center's right here, and it obviously is split between these 2 numbers, which depends on theta. And so the variance isn't telling us the information about this location parameter. So let's just see that technically, that when I integrate, I try to come up with this distribution, FR, given theta, all I have to do is integrate m out of this joint distribution. And I have to be careful of where m lives. Theta plus r over 2, theta plus 1 minus r over 2. This integral couldn't be any easier because everything is a constant with respect to m. And this is just going to look like this. n minus 1, r raised to the n minus 2, m, where m goes between theta plus r over 2, theta plus 1 minus r over 2. So that's just n times n minus 1, r n minus 2, theta plus 1 minus r over 2 minus theta plus r over 2. So what we notice is that the thetas cancel each other in this equation. That's the important bit. So there's no thetas in this equation. This is the key point. If you want to wrap up the algebra, you can. No problem there. So, but this does not depend on theta. That's supposed to be important. So we say that R is ancillary. Don't worry, that's fixable. Gotta get some glue. So thetas cancel right there. Does not depend on theta, so R is ancillary. That's true. And so I might mess up right here in the way that I phrase this, and I might say something like, R has no information about theta, but as we've already figured out, R is part of the minimal sufficient statistic. And if I throw it away, and I just use the mid-range, I'm losing information. So I can't re-figure out what the min and the max are. There is information about theta on its own in the mid-range. So if we did the integration the other way, we'd notice that the mid-range still has information about theta on its own. So it's not ancillary. So we just write that down. Note, M is not ancillary. And you can probably recognize this just by changing that integration to R, integrating between 0 and 1 right here, but retaining the information in where R depends on M. So R has some relationship with theta. So let me just remind you, this mid-range is going to affect our integration bounds. So we don't integrate just between 0 and 1 when we go to integrate out R, but I have to integrate using these bounds. So I need to shuffle this equation around, solve for R, and that's going to depend on theta and the bounds. And theta will appear in the integration once I integrate out M, or once I integrate out R. And we'll find out that M is not ancillary. We can just look at this example and figure out real quickly conceptually, the mid-range is somewhere around here. It's between those two numbers, and that's certainly influenced by theta. If I changed theta and I shifted this thing around, then the mid-range would be some estimator of theta. It's not perfect because it's not min sufficient. It doesn't have all the information by itself. I need R to figure out what xn and x1 are. But R on its own has no information. So that's what Basu's theorem is all about. So you might be inclined to think, and I think I thought this at one time, that R, or an ancillary statistic, could never be used. So it wasn't useful. But in this example, you can see that it's definitely useful. Let me show you just a little bit more, build on this example just a little bit. Let's look at it in a discrete case. I think there's a paragraph in your book about this case. So it's worth going through. So here's a new example. This is the same example in disguise. So I'm going to say probability x is equal to theta is equal to the probability that x is equal to theta plus 1 is equal to the probability that x is equal to theta plus 2. And I'll tell you what these probabilities are. They're each a third. So they sum up to 1. So I add these things together, they sum to 1. So I could write probability of x taking on any other value other than theta, theta plus 1, or theta plus 2 is 0. And if I were writing a book, I would write that. So, but it's pretty well implied since you can't have negative probabilities. So x is uniform. And theta is acting as a shift parameter in all of this. So the length of that is just a little bit different. But in disguise, this problem looks very much like the problem we were just solving, the continuous analog. So let's just analyze some cases in here and convince ourselves that R does have information about theta, just not on its own. So in this example, R is ancillary and M is not, for the same reasons that we just showed here. So I'll just write down R is equal to xn minus x1 is ancillary. M is not. Not ancillary. Together, these are minimal sufficient. For the same reasons as we discussed in the continuous problem. So let's just look at some cases. So cases. We could look at when R is equal to 0, R is equal to 1, or R is equal to 2. Those are the three things that can happen. And there's certain possibility for what M is. So when R is equal to 0, that means that I saw two draws from this distribution. Could draw theta, theta plus 1, theta plus 2, 1/3, 1/3, 1/3. Across the top. And so if the range is 0, then it means that I got a repeated value. So it could have been that I saw this number twice, or I saw that number twice, or I saw that number twice. And so the mid-range can be a lot of different things. So the mid-range could be theta plus theta over 2, theta plus 1 plus theta plus 1 over 2, theta plus 2 plus theta plus 2 over 2. Calculation was obvious. I probably should have just written down what those mid-ranges could have been. And so the interesting question to ask is, what's the probability of this happening, that happening, or that happening? They're all equally likely because it's a uniform distribution. So each of these happens with probability 1/3. Semi-informative. What if I saw that R was equal to 1? The mid-range could be theta or theta plus 1 divided by 2, or it could have been theta plus 1 plus theta plus 2 divided by 2. So this is equal to theta plus 1/2, and this is equal to theta plus 3/2. And that's semi-informative about what theta is. So this happens with prob. Each of these 1/2. They're both as likely as each other just because this is a uniform distribution. Here's the really informative case. So if the range was 2, there's only one possibility. This could be the first draw was theta, or one of the draws was theta, and the other draw was theta plus 2. Divided by 2, that's equal to theta plus 1. And this happens with probability 1. So in this case, you know what theta is. So you can kind of see the information propagating in these different cases. R is telling us something, but we need to know M for it to be useful. And so in this case, R is equal to 2. Somebody tells me that, I get real excited as a statistician. If somebody came to me with this problem, and I'd say, tell me M real quick, and I'll tell you precisely what theta is. And none of you would be wowed by my probabilistic ability by doing that. I would just take M minus 1, and that would be equal to theta. And it would be certain. And so R's telling me something on the lead-in. I'm going to be sure about this once you show me M. Or I'm going to get the answer right half the time if I had to pick. Under this case where R is 1, or if you told me that, I'd go, oh shucks, we got really unlucky. I'm going to be able to give you theta with probability 1/3 once you tell me what M is. But there's information in there. So Basu's theorem concerns this situation. And the question is when does an ancillary statistic have information about theta? On its own, never. In the presence of other things that I can use in the minimal sufficient statistic, might have some information. And our example shows you a good case of this. The question, when might an ancillary statistic have info, and I mean about theta? There's two answers to this question. One answer is on its own, never. So let me just say this. Answer 1, on its own, never. But in the presence of something else, it might be useful. might be useful. Here's an example of that. Ancillary statistic in the present and something else, it's going to definitely lock down information for us. In this case, you tell me r is equal to 2. I'm waiting to hear m, and I'm going to tell you with certainty what theta is. So r was helpful for me to discern that. On its own, can't be used. In the presence of something else, it was useful. Sometimes ancillary statistics you can't do anything with, and it'll never be useful to you. So the condition we need to study is completeness of a statistic. So let me just write down what that is. Actually, let me tell you what Basu's theorem is first. I'm going to use completeness in my definition, and then I'll tell you what completeness is. Maybe that's a better way to think about this. So completeness is the condition. I'm going to invoke it, and then I'm going to tell you what it is. So if a minimal sufficient statistic and I'm going to call this T of X. That's what we used before. Is complete. Then it is independent of every ancillary statistic. For data that's created under the same model, obviously. So it's this condition that tells us, let me interpret this for you. So it is independent of every ancillary statistic. That means that it cannot be used to inform you about theta. So that's what this says. Cannot be used to inform theta in the presence of something else. So my other data in this example we studied was M. So I could use it to rebuild the minimal sufficient statistic. And so sometimes we just write this down. I'll give this a name, our ancillary statistic. Let's call that S of X. And so the notation that some people like to use is that if this is true, then S of X is independent, orthogonal to every other statistic that has the information. So that's kind of neat. I think that this can be useful. Right here, I've never seen anybody tell me how to use this in practice, but there is something called the conditional frequentist. And conditional frequentism has to do with conditioning on the right ancillary statistic. And that's an interesting thing. The problem is trying to figure out what the right ancillary statistic is that you should condition on. I don't know a paradigm of thought for how to do this. So I think conditional frequentism has been virtually abandoned, although it's interesting. I do like conditional inferences. So I like using likelihood functions. And so I'm always conditioning on the right stuff. But that aside, because I don't know how to teach it, because I don't know how to do it in practice, this is an interesting mathematical statement. So Fisher back in his early days is he was trying to understand properties of statistics. And so he understood what was important about a sufficient statistic, a minimal sufficient statistic, but it begged the question of what's the other part of that space where all the other information in the data is coming from. And you'd be inclined to say it's where the space where the ancillary statistics live. But these are only orthogonal to each other and they don't overlap each other if we have this condition, completeness. So let me tell you what this is. Oh, and let me just say, this is Basu's theorem. So that's pretty cool. The mathematician in me really thinks this is interesting. The statistician in me, the practicing statistician, makes me think, I wonder if this is useful. Do I need it? And I think the answer is probably don't need it. But here's what a complete statistic is. There's a rub here. Okay, so Tx is complete. So what we might do is check to see if our minimal sufficient statistic is complete, and then we would know all other ancillary statistics don't overlap the information. It's interesting. This is true if, so this is the condition, expectation of gt of x, so this is some function, there is a little criterion on this. I'll say what it is in a second. But the expectation of this, conditional on theta, is equal to 0, implies that the probability that GTX itself is equal to 0. This is equal to 1. Okay, so let me read that to you again. If this is true, the expected value of this thing right here, this transformed value, so this is a function over a function, is equal to 0, then that thing is 0 in the first place. So that's another way of reading it. And this is a probability statement about it being 0. So it's not necessarily 0, just in probability it's 0. Compared to everything else, it's so vacuously small that we call it 0. So that's what this is. So this is a probability statement about GTX being 0. But if I expect it, this function, to be 0, then the thing that I'm doing in the first place, computing GTX, what I did is I computed 0 in the first place. So if the expectation of the thing is 0, then the thing itself is 0 in probability. So that's a small caveat. There's an implication right here. So this right here is measuring something. And so if we're going to make a probability statement about it, it has to have a probability distribution. It has to be a measurable function. So I think that's implied by the definition. So G right here is measurable. i.e. we can measure it. There's an inverse map to the random variables that created it. I can measure their probabilities, add up all of those probabilities, different ways of forming this, and I can tell you what the probability of GTX is. In particular, I can tell you that it's probably 0, is what this statement says. So, inverse mapping back to the original random variable. We had a lecture on that concerning dice throwing. But the word measurable just means that I can measure it. I know what's going on with the random variables, I know what their probabilities are. They created it. And so this is hard to play around with because nobody tells you what G is. And so this is going to be for all measurable g's. So that's what we're looking for here, is I need to entertain every g function out there. You know, smooth, continuous stuff is always going to work for us. Just don't have this thing so erratic that I can't measure it. So not those functions. So, well-behaved stuff, it's measurable. I can tell what's going on with it. So I need to be able to prove this for any g. And I have to figure that out, that this is a true statement for all these infinite collections of g functions. And that can be hard. So I assigned a book problem in Casella and Berger. I forget which number it is, but in chapter 6, and it gives you some statistic and it says prove that this is complete. I think it's for a binomial distribution. Prove that the sum of the xi's is a complete statistic. And so that's cool. So no ancillary information could ever help me out. So if somebody happened to hand me ancillary statistics, I can throw them away. They'll never be useful to me. So, but if somebody said, hey, I'm never going to give you the minimal sufficient statistic, but I'm going to give you some ancillary statistics and I'll give you some other statistics as well that do have information about theta, I might ask in a hypothetical case like that, is the minimal sufficient statistic complete? And if they said yes, I'd throw away all the ancillary stuff. If they said no, I'd hold on to it. So this is a complete fiction. It's never happened in my statistical life. Proving this statement for all g functions can be complex. So I'm not going to use your mental fuel to entertain this any farther than knowing what the definition is and knowing what this statement says, and then the one homework problem. So I won't be testing you on being able to prove this statement in particular examples, because I think it can be really tricky in a lot of cases. So truth be told, if you just came up to me and you asked me to do this for any particular problem, it would take me a while. And so it would even take me a while in some of the simpler cases. So I think that's it for now. We're going to pick up next time with point estimation. What I would like to do is return to the coin flipping model. And I'm going to start out by entertaining 3 different paradigms. Moment-based estimators, likelihood-based estimators, Bayesian estimators. And I'm going to show you what they all do. In the lecture after that, after we cover an example with coin flipping, I'll generalize everything for you. I think we've already done a lot of this work. So we spent a lot of time, building up Bayesian analyses, at least in one particular example, but we've talked about them in pretty good detail. We've looked at likelihood functions a lot already, so I think we're raring to go, and chapter 7 is going to be pretty seamless. So anyway, you guys, sorry for what's going on, but I think moments like these, we just manage. I'll be here available to you. If you have any big concerns, send me an email and I'll jump to it and answer for you. So hold on to those midterms. If you see me around and you want a grade, I guess we can simulate that. I wonder if it'll happen. So, saying that, midterm 2, I'm going to probably give you a time limit. I'll probably issue the exam to you and give you a day to finish and then return it to me. So some reasonable window. If you're having electronic difficulties, let me know before that and I'll accommodate you in any way that I can. So I hope you're well, I hope you're healthy, and I hope you stay that way. So let's follow all the precautions that everybody tells us, limit the amount of contact that we have with everybody, and I think we'll all be fine. So until next time, you guys, that's it.